Splunk is able to generate complex statistical information, correlate disparate events, etc. But what if we want to map the state change of a sequence of events? Using eval, we can calculate information about the state of a system or something else based upon the contents of a particular event. We could even combine this with commands such as streamstats or external enrichment sources, providing the means to understand an abstract notion of state, comparing it to the previous event even. However, such an approach fails to scale or be generalized, and it doesn't lend itself to the analysis of a path taken in order to get to a particular state. From discrete mathematics, there's the notion of a finite state machine, which enumerates all possible states something can be in and the conditions under which they can change. In the literature, they are often used for evaluating the properties of a given design specification. Examples of this include things like industrial control systems, security protocols, etc. From these specifications, we can form graphs of possible paths or sequences of expected or permitted states. When applied to the domain of security research, the literature often refers to them as attack graphs, and I'm just showing an example of an attack graph in the literature here. Essentially, we can see a begin state and then a sequence of events that lead to an end state, and we refer to this as a scenario. So what if we could take a specification like this and overlay it to a real system, logging events into Splunk? Using Splunk's SDK, I've written a new streaming command called sequence, with which we can do just that. We can use this to perform previously impossible analysis and detection of the tree depth, that is the number of states that have been traversed, and the actual sequence of events that has been taken, and this is also known as counterexamples. I should mention though that although we're using a security example here, this also applies to other use cases outside of security. So let's look at an example finite state machine for this demo. So here is a very trivial finite state machine. We can see a start state, which in this case is going to be a user logging in, and then we can see arrows, which are referred to as edges, which will cause transitions to different states, or these circles here. And we can see that not every transition is possible between each different state. It depends on the conditions under which those transitions occur. So if we have a state machine like this, and we want to encode it into our new Splunk command, we need to provide a specification. Here we have the example model, and the scope here tells us that each time a unique source type host user and session is seen, a new finite state machine is going to be created, and the constraints upon which the creation of a new finite state machine is made is the source type being Linux audit and the type of event being a user login. So the type here is just a field name, and this is the value of that field. Then we have the possible states of the model, and there must always be a start state. In each state there are possible transitions. That is, if we come back here, these arrows here are the transitions. So from the start state we have three possible transitions: crash, sniff, and sudo. If we take the crash example, the guard here, which is essentially a predicate or a condition upon which this transition will fire, is that the type field must, of the next of a subsequent event, must have this value. If it does, then this transition takes place. So we will transition from the start state to the process crash state, which we can see defined here. So this is describing this edge here to this new process crash state. If we come down here, we can see that process crash has one transition, and if this event is seen, then it transitions into a subsequent state. That state, as we see down here, then has no transitions. In other words, that is an end state. And so this model describes the diagram that we're seeing here. Using the sequence command, we can then overlay that model on top of events coming into Splunk. Here, I've created a pseudo events that mimic Linux audit D events to the extent that's required for the purposes of this demonstration. And essentially, we can see login events, we can see user commands, that is privilege escalation using sudo, TTY events, which is keystroke logging, more user events, and network cards being put into promiscuous mode. And then finally an event that doesn't belong in the model, and that's there for a very good reason, and we'll see why in a moment. So let's apply this model. So if we type sequence, then we need to provide the name of the model, which was example. So this is going to provide us with two things, the state and the depth. The depth is the number of states that have been traversed in the graph, and the state is the current state in that particular event. So we can see start, escalate privileges. If we come back here, we can see this state here. And then finally we can see another state here. And furthermore, if we look at the depth, we can see that a depth of 0 is start, and then 1, and then ultimately 2. Now, it's important to note that there are various things going on here. Alice has two sessions, session 1 and session 2 on this particular host. That's why the depth is 0. Then, in Alice's first session on DB01 host, she escalates her privileges with this command, so the state changes, and we can see the depth incremented to 1. The next thing that she does in that session, the next thing she does in that session is this command here. However, this is an important demonstration of where an event is part of the finite state model, but there's no transition guards that are able to fire, and so a transition doesn't occur. The state remains the same because there's no TTY in the definition of the model. So this is desirable. However, the next event for that same session of Alice's on that host, we can see that there was a transition occur, and so now we have a depth of 2, and the state has subsequently changed. Importantly, the model has also completely ignored this event at the bottom. The reason for that is that the constraints here were not met for this model, and so it just passes the event through the pipeline. However, we can specify counterExample equals true and get even more information about the path that was actually taken. So in this case, we can see that at step 0 we started, there was then a transition to step 1, escalate privileges, step 2, promiscuous mode. And so we could potentially write a where statement here and put some conditions upon which we would trigger an alert or whatever it might be. There's various things that we could do with this counterExample field. The counterexample essentially answers the question, what happened? How did we get here? In the past, we could see the event, but the counterexample shows us the sequence of events that gave rise to that event. So it's quite a new way of looking at detection and analysis in Splunk. Also, because the sequence command ignores events like this at the bottom that don't meet the model's criteria, and it's a streaming command, we can pass the events, so the generating command at the front can pass events from various different sources or source types to multiple sequence commands in the pipeline for different models. So let's say if you had two different types of PLC, you could have two different models, and those models would apply to the correct source type, and then you could pipe that to some conditional, let's say it's a where statement, that makes some comparison between the behavior, the concurrent behavior of two different devices. So we can examine those compositional properties of these distinct components interacting in real time and whether or not they are actually holding certain desired emergent properties. It's incredibly powerful potential. And this command also opens up new opportunities for the application of glass tables in ITSI and enterprise security. For example, using glass tables, we could show state changes visually, and in a SOC environment that might be really useful, or if we're looking at certain components in our infrastructure, the state changes, particularly based upon counterexamples, may be of great value to operational staff. I hope this has been an interesting and valuable video. My apologies about my voice. If you're interested in the sequence command, please look for it on Splunkbase soon, with the name of the app will be TA-state machine. Thanks.